The Bernoulli distribution is a very, very simple, discrete probability distribution, one where only two possible values, so a bit like binary, where 1 will represent success, 0 will represent failure. The only two possible outcomes. So we'll let our random variable x be the Bernoulli random variable. So the experiment is sometimes called a Bernoulli trial. Its probability density function is a very simple probability density function. Probability of p when x is 1, therefore it's 1 minus p when x is 0. For everything else, probability is nothing. Could also express it this way. Probability that x is equal to little x would simply be the probability p to the power of x, and then the probability 1 minus p to the power of 1 minus x. So if I draw up our table for this one, and I'll need to work out the mean and the variance, so I'll need my xpx and my x squared px. So our expected value is p. The variance, when we work it out, the expected value of x squared minus mu squared is p times 1 minus p. So if we know that our random variable is a Bernoulli distribution, so we just write Bern, the only thing we're really interested in is the probability of success, so p. So we write Bernoulli and the probability of success. We know the expected value is p, and we know the variance will be p times 1 minus p. So that's for a Bernoulli distribution. So that then brings us to this idea of binomial probability. And a binomial experiment is where we continually repeat the Bernoulli trial over and over and over again. So we do it the first time. There's only two outcomes because it's a Bernoulli, so it's either A or B. Probability of A happening is P. I'll call the other one Q rather than writing 1 minus P all the time. So the other one is Q. We repeat the experiment. So now we might have got AA or AB, but we also might have got BA or BB. And the probability of those would be P squared, PQ, PQ, and Q squared. I repeat it again. So AAA, AAB, and so on and so on. Probabilities for each of those, PQ, P squared Q, P squared Q, PQ squared, P squared Q, and so on, down to P cubed. What the heck, let's do it one more time. Then there's 4 AAA, AAB, ABA, and all the way down to probability of all those, p to the power of 4, p cubed q, p cubed q, p squared squared, say that one again, p squared q squared, and so on and so on and so on, till we get q to the 4. A familiar pattern emerges. See, when there was just one thing happening, probability of A was P and the probability of B was Q. When there were two things happening, but I'm not concerned with the order, now it looks a little bit more interesting. Because look at that middle one. Instead of just saying probability of AB, we just want, no, A happened once, B happened once. So I might have got AB, I might have got BA. There were two ways I could do it. And I get 2PQ. If we look at 3 events, same idea, and we start recognising each of these to be something we've seen before. So 3P squared Q, 3PQ squared. Okay, well 4 events. Again, just interested in how many times the thing happens, not the actual order. Hang on, where have we seen that before? How many times something happens, not the order? Well, now we're back to combinations. And it's not a coincidence. 3, 3, so these are the binomial coefficients that we saw back in the binomial theorem, which turned out to be combinations, if you recall. That makes it a lot easier now to find these problems, because we can say, well, if my random variable is a Bernoulli trial, if the event happens exactly k times, when I repeat the experiment n times. And it ends up being, basically, it's just the general term of a binomial expansion. So NCK, the way I always think of it is the probability of it happening to the number of times it happens. So p to the power of q, then therefore q must be to n minus k, 2 have got to add up to be 1. Biggest mistake on these is forgetting the binomial coefficient, because there are different ways. We're not interested in the order they happened, just how many times they happened. Q, remember, is simply 1 minus p. Okay, let's do a few. We've got a bag, 30 black balls, 20 white balls. And of course the key with this is without replacement, because we're repeating the same experiment over and over and over again. So if we pull it out and don't replace, then the probability is going to change each time. So it's no longer the Bernoulli experiment. We just got to go back to basic counting ideas and things like that. So it's got to be with replacement. All black, well, that one's probably simple, but let's do it using this idea. So X is going to be the number of black balls that are drawn. That is what we're interested in looking at. So X equals 7 will be 7C7, probability of it happening to the power of 7, therefore probability of it not happening to the power of 0. That would be an exact unsimplified answer, and the one down below is the exact simplified answer, I guess you would call it, because that doesn't simplify down. There are no common factors there. 4 black balls. So, okay, X equals 4 will be 7C4. Don't forget the binomial coefficient. Probability of it happening to the power of 4. Probability of it not happening then to the power of 3. There is our unsimplified answer, which works out to be that. We have an election. 30% of voters favour party A. An interviewer is going to randomly select some people. What's the probability that 3 of these people favoured party A? So X, what I'm interested in looking at is the number of people that favoured party A. So probability that X was 3, 5C3, probability of happening to the power of 3, probability of not happening to the power of 2. Unsimplified, which works out to be 1,323 on 10,000. Majority favour A. It's still the same probability ideas. So X is greater than or equal to 3. Well, that'll be 3 do, 4 do, or 5 do. So I do each one of those, add them together, and there we go. We get 4,077 over 25,000. At most, remember, at most, at least usually gives you a clue to, hey, let's use the complementary event idea. So I'll go 1 minus what we've just worked out. That's going to save me some time. And we get our answer. Okay, here's one from an HSC. There are 5 matches on each weekend of a football season. Megan takes part in the competition, gets 1 point if she picks half of the winning teams for a weekend and 0 points otherwise. Very strange rules for a tipping competition, but there you go. The probability that she picks a correct team is 2/3. So the probability that she gets 1 point, they're telling us, is going to be 0.7901. We've got to show that that is indeed the correct answer. So what am I interested in for this? It's the number of matches that she's picked correctly. That's what I'm interested in. In order to get a point, it has to be the majority. So 3, 4, or 5 matches correctly. So I work out each of those individually, add them together, and sure enough, that works out to be 0.7901 to 4 decimal places. Okay, second part of the question. Well, hence find the probability that Megan earns 1 point every week of the 18-week season. So this is something new we're interested in. So I'll introduce a new random variable. Why? What I'm interested in looking at here is the number of weeks in which she earns a point. That's what I'm interested in looking at. And we just calculated the probability of that. So we want y equals 18. 1 point every week. 18C18, but the probability we're now using is the one we just worked out, because that's the probability that she earns a point. So 0.7901 to the power of 18, and the other one obviously to the power of 0. We get 0.01 to 2 decimal places. Find the probability she earns at most 16 points. So at most, there's those keywords again. So we just worked out 18, but we're going to need to work out 17 as well for this one. But at least there's only one thing I've got to work out rather than working out 0, 1, 2, 3, all the way up to 16. And we got 0.92. Big city, 10% of the population has green eyes. Probability that 2 chosen people have green eyes. Probability that 2 are green. This one's not a binomial probability question. This is just a simple probability one. We're going to choose 2 random people, and they both have green eyes. I suppose you could turn it into a binomial one, but 0.1 times 0.1, 0.01. What's the probability that exactly 2 of the group of 20 have green eyes? Now we've got our binomial probability question. We're interested in looking at the number of people with green eyes. We want 2 of them, but 2 from 20. So 20C2.9 is to the 18.1 squared, and we get 0.285. What's the probability that more than 2? More than 2, let's work out the complementary event, going to be easier. 1 minus probability of x is less than or equal to 2. Got to work out those 3 individual ones. Subtract from 1, 0.32. Okay, so that's binomial probability and Bernoulli distributions.